So before I begin, just a quick medical disclaimer. This talk is for educational and informational purposes only and may not be construed as medical advice. The information is not intended to replace medical advice offered by a physician. I am not a doctor, so just want to make that very clear. So a little bit about me. So my name's Antonio and I'm the one on the top, in case you're wondering. This was in Komodo Island. I took the photo last year during the summer. So I was born in Manila, but I grew up in Tokyo. And I studied chemical engineering before coming to Code Chrysalis. And I ran track and field and I played football in high school. And that actually relates to how I chose my topic of heart rate variability. Now you might be wondering, I don't see the connection. So let me walk you through it. So when I was an athlete, I would practice for maybe 2 hours, every day in order to get better for my sport. But the thing with your sport, and if you practice, is that you have 2 hours of practice, but 22 hours where you're not training. And those 22 hours are pretty important. What you do in those 22 hours can affect how you perform the next day. So things like recovery, getting good sleep, eating well is important. And one way to track recovery is heart rate variability. So I came across that 6 years ago, but I ran into some roadblocks that stopped me from pursuing this. So first was, I was limited by the expensive equipment you needed back then. You needed a dedicated machine that was a bit pricey for a high schooler, and there was some proprietary software that you needed to use in order to use the machine as well. So I kind of left it at that. But recently, there's been a lot of newer and portable hardwares that have been developed, and I know how to code, so I wanted to see if I could revisit this problem and attempt to do it on my own. So for those of you that are wondering, what is wearable tech? Because that is the hardware that has been developed that I'm referring to. So it is any device that you wear that can send or receive data. So how many of you have a wearable tech with you right now? Just a show of hands. A couple. So things like an Apple Watch, the Fitbit, Samsung smartwatches, they're very common. They're not the only ones, but they're one of the more popular ones in the market right now. And there are a lot of reasons why you use or have wearable tech. And one reason is just the sheer amount of health data you can get from it. A phone's great for getting how far you walk, but when you have an actual smartwatch on you, you can get so much more data. Heart rate, activity, things like that. And it allows you to log this data over time so that you can see your trends. Maybe you're a bit frustrated that you haven't been losing weight or being as active, but if you zoom out of maybe a week and look at it in terms of months, and you're seeing progress, that can motivate you to keep doing what you're doing. And it gives you accountability and information about your own health. So, what is heart rate variability? This is why you're here, right? So it's the variation between your heartbeats. Specifically, it's the beat-to-beat difference in time. So if you think of a metronome and you set a particular tempo and you time the time between each tempo, you're gonna have a very consistent time. And because it's very consistent, the variation in that is going to be low. On the other hand, if you have a heart condition like arrhythmia, where you have irregular heartbeats, the beat-to-beat time in one instance is going to be different than in another. So why is heart rate variability important? So I want to ask you guys a question. What controls our heart rate? Any ideas? Okay, well, if you guessed brain or your nervous system, you're on the right track. It's pretty much modulated by our brain and central nervous system. But is it voluntary or automatic? I hope you guys say automatic. If it's voluntary, you need to talk to someone because they would probably discover something new. So what does this mean though? What does it mean that our heart rate is controlled by our brain, but it's automatic? So it means that our heart rate is generally a response to our environment. So if you're exercising, if you're running for dear life, if you're giving a public talk, you're probably going to have a high heart rate. On the other hand, if you're sleeping, if you're watching Netflix, if you're just lounging about, you're probably going to have a low heart rate. So heart rate variability is a good proxy for measuring these involuntary processes that happen in our body. What do we mean by involuntary? So what we control is our skeletal muscles that help us move, talk, make facial expressions. But aside from that, there's a lot of things going under the hood in our body that we don't actually control. So things like the smooth muscles for your digestion, that's not voluntary control, or the cardiac muscles that cause your heart to beat, they're also not controlled by us. So heart rate variability can track how this autonomic or involuntary process is running. And these processes can be divided into two general responses, sympathetic and parasympathetic. So the sympathetic is your fight or flight response. It is purely survival. So you'd have an increase in heart rate, your blood flow increases, your breathing rate increases. You want to get as much blood into your muscles as possible so that you can do something, whether it's run or fight. But when this happens, your heart rate variability decreases because you want your heart to be as consistent and as mechanical as possible. On the other hand, the parasympathetic response is your rest and digest. So think about after eating a big meal or winding down before going to bed, you're going to have a pretty relaxed and decreased heart rate, and your variability increases because your heart isn't under any stress. It doesn't have to force blood to your body like if you were in a stressful situation. So we know that a high heart rate variability would suggest that you're well rested or you're relaxed, and a low score would be more of a stressed or you're still recovering state. So how is heart rate variability measured? Does anyone know what this thing is or have seen it before? So it's called an electrocardiogram or an ECG machine. And what it does is it hooks up pads to your chest to measure the electrical output of your heart. So you'd see this in your doctor's office. And this machine can measure the electrical output with respect to time or frequency or other nonlinear methods. But time is the most common, and that's the one that I was using. So how can you obtain this ECG data? Well, if you go to a doctor's office and get your checkup, you can get it there. But the problem is it's very inconvenient. Every time you want to get it, you have to go to the doctor's office. So there are some alternatives, such as a chest strap heart rate monitor. And it's good because it still measures the ECG readings from your heart because it's mounted on your chest. But if you're wearing this the whole day, it can get pretty cumbersome. So if you guys have been noticing the trend, there is wearable tech, such as smartwatches, that can do this for you. So it's pretty novel in that it can read these signals from your wrist instead of having to be mounted directly onto your chest. So let's look at how the Apple Watch does it. So it's integrated with the Health app, and the ECG data can be recorded with a Series 4 or later watch in supported countries. And you use the ECG app to take a 30-second reading, and depending on where you're wearing your watch, you use your other hand to hold the dial, and that creates a closed circuit, which allows the watch to read the electrical current from your heart. And this data is stored locally, so if you want to access it, you have to export it from your watch or phone. So here's a list of the countries that support this feature. Right now it's 32, and if you notice, there's no country that begins with J. So it's not supported in Japan yet. I'm not entirely sure when they'll decide to implement this feature, but I had to work around this situation because I have no access to the ECG data from an Apple Watch. So luckily, there are publicly available data sets that are used for research purposes. Specifically, I used the MIT BIH arrhythmia dataset or database, and it has 48 samples of 30-minute ECG readings that are sampled at 360 hertz, which means 360 samples in 1 second. So very long data sets, very high resolution, so it's great for analysis, but it's probably a bit overkill. So you're probably wondering what this ECG data would look like. It's going to be a long column of numbers. So the first column would be the time or sample number, which is the instance in which a current is recorded. And then you'd have the electrical signal strength in the second column. You might have the date or time of reading either in the header or the file name. And this file is generally stored in a comma-separated value or CSV file. So the fun part is trying to obtain heart rate variability from ECG, or turning this into that. So how do we do that? Well, first thing is you need to set up the data to be in your device. So you need to acquire ECG data either from your wearable tech or a data set as in a CSV format. And you need to put this CSV file in the same directory as whichever coding environment you're working with. So let's say it's there, and we need to use a CSV parser, which is a program that can kind of go through the CSV file and take the values we want. So in this case, we just want the middle column, which has all our data in it. So to do that, we need to separate the entire file by commas and line breaks and just get the electrical signal column we want. Once we have this data, we can put it into an array for easier usage so that we can plot it or do operations to it. So let's say we do that and we plot our ECG data, and this is what it would look like. So one of the things you'd notice are these really sharp peaks. They're called the R peaks. So there's 7 of them in this graph. And if you remember what heart rate variability was, it's trying to measure the time, the variation in time between heartbeats. So these coincide with our heartbeats. So the next thing we need to find is the time between beats. That's called the RR interval, or the time between each interval. So in this case, there are 6 interval times from 7 peaks. So if it's hard to follow, you have 5 fingers and 4 gaps between them. So let's say we are able to do that. We need to process the data, and that involves finding the mean or average and the standard deviation. It's a bit heavy on the math, so I came up with a couple analogies to make it easier to understand. So this is a bullseye or a dartboard, and the mean is where your data is clustered or centered on. So if I shoot a couple times, you can see that my mean is somewhere over there, right in between where the middle of those data points are. On the other hand, standard deviation is the spread of the data from that particular center. So if I try again with green, you'll notice that the mean is actually pretty similar, but the spread of the data is a lot wider. So this has a greater standard deviation than the red. And finally, these 2 concepts, mean and standard deviations, they don't necessarily have to be a real value, but what they represent is what's important. So for instance, if I try to shoot a bullseye and I'm off to the left, and I try to shoot again and I'm off to the right, my mean is actually the bullseye, but I didn't actually score it, so that doesn't count. So first thing is getting the average RR interval. So we need to get every instance of the RR interval, sum them together, and divide it by however many we have. So if we look at our previous example, we have 6 RR intervals, so we add all 6 and we divide by 6. Standard deviation is a bit trickier because there's more math involved, but it generally boils down to finding the difference between something. So the first one is the standard deviation of RR intervals. But if you look into the literature, you'll see it as SDNN, which just stands for normal peak. So if you turn the data to normal, it becomes N. But the idea is within each RR interval, you're trying to subtract it from the average value we calculated earlier. There's another one, which is a bit of a mouthful, but it's the root mean square of successive differences. So this is the important part, successive difference. It just means that you're trying to find a difference of the interval with respect to the one coming after it. So it's just looking at a relative difference. So how do we find the RR intervals from our array? So this is it visualized, and it's actually pretty easy to see it when you look at it. But trying to find it from an array is tricky, and that's where different sorting algorithms and data processing comes in handy. So there's at least 7 different algorithms that medical professionals have developed to analyze ECG. So there's plenty of scripts out there to do it for you. And the other thing is we need to know the sample rate of our data. So right now, this only represents the distance in terms of indices from each data set, but we need to know how much time is in between. So once we know the sampling rate, we can calculate that easily. Then this is just a simple iteration where you find a difference between each value. And once you have your RR intervals, you can solve for the 3 equations. So let's take a look at that. It seems a bit abstract, but once you see it, I think it'll make a lot more sense. So we'll have 2 data sample sets that are 30 seconds long. So we have sample A and sample B. So what you'll notice relatively easily is that there's definitely less beats in sample A than sample B. But that's probably it that you can tell from just looking at it, which is why we do these math operations to give us numbers. So we can see that, yeah, sample B is definitely faster in terms of the average beat-to-beat difference. And the variations is actually greater in sample A. So there's more variation between each beat. So what does that mean? So given our current data set, all the results are in times of milliseconds because we're still looking at the difference in time. If we have the average hour interval, we can actually calculate the instant pulse or beats per minute of the value. So in sample A, it comes out to 60 beats a minute. And in sample B, it's closer to 91 or 92. And then there are these two values, the successive differences and the standard deviation. These two values both measure variation, but which one is better? Because they're both valid values for heart rate variability. So standard deviation is good for a longer duration sample because you have a lot of data sets, the mean becomes more relevant. But the successive difference is better for shorter samples because you're only comparing a relative difference from each RR interval from one to another. So think of the bullseye. If you have a lot of data sets, the standard deviation is the way to go. And if you have very few, the successive differences is a better choice. So let's take a step back and understand why we went through all this effort. So we know that heart rate variability is a great proxy for monitoring our health and the autonomic nervous functions of our body. And it allows us to engage in something called biofeedback, which is changing our behavior based on something we're measuring. So if our heart rate variability is quite low right now, meaning we're a bit stressed, something we can do instantly is just take some deep breathing exercises to relax. And then on a longer time scale, maybe alter how we're behaving. So maybe increase our sleep, do some more exercise, things like that. And it allows us to quantify these intangible variables such as recovery. It's hard to say, oh, I'm kind of recovered today or I'm very recovered today, but having a number makes it a lot easier. But heart rate variability is not perfect. So things like our sampling errors. So based on what device we use to measure the ECG, it might not be a reliable data point. Also, the consistency of our data. If we are very consistent in measuring it every morning or every afternoon at the same time with as much of the conditions similar as possible, then it's more useful. But if you're kind of taking it whenever, it's not as useful. Again, quality of data. So this ties in with which hardware you're using. And data validation. So let's say you have an ECG value or heart rate variability value from your watch, but it would be the same as if your watch was a couple of minutes off. The relative value will be meaningful, but in terms of an absolute value, it's not precise unless you validate it by going to a doctor's office to see that the numbers match. So in terms of wearable tech, they're very convenient. You can measure a lot of things. It gives you a lot of easy access to health metrics that you can use, and it gives you a good reference point for what is good health as a general guideline. But it is not a substitute for medical advice. So always go with your doctor at the end of the day. And there's also a lack of standardization and personalization with health tech. So let's say Apple has the SDNN as their way of calculating heart rate variability. Fitbit might choose a different method, and they're both valid values, but because there's no regulation about which is what you should use, it's hard to tell or to compare between different users. Finally, there's also outliers not being accounted for. So if you have a benign heart condition, this might not be useful for you, or if you have any other health condition that isn't really accounted for in what a standard health would be, these wearable techs are still not personalized to the extent that you could use it or benefit it as much as the average person. Another point is data privacy. So once you export the health data in your Apple Watch to your laptop or you put it on the cloud, if there's a breach, it's gone. There's no authentication or extra layer of security for your health data. So it's one thing that people need to account for. And finally, more data does not mean better health. So at the end of the day, you can have as many health metrics telling you all about your health, but if you don't do anything about it, it's pretty much useless. So two things I want you guys to take away from this talk is that heart rate variability is a useful tool for tracking your health, but it has its limitations as a metric and getting accurate readings. So thank you for listening. Here's the link to the GitHub repo.